Okay. So, from the last lecture, if you use the time frequency sampling, that constant, that we said that LW, the dissemination in time should be less than equal to 2 pi by the bandwidth of the analysis window, and we said that NW, or you can say 2 pi by NW must be less than equal to 2 pi by N. Okay. So, what it is said that basically that complete recovery of the signal is possible if I choose the window whose length is NW, which should be less than the number of DFT I have taken N, which define the number of channel. And so, if I say that I have a 16 kilohertz pitch signal, and if I take 20 millisecond window, so length of the signal is nothing but a 320 sample. If I take the DFT length, N is equal to 512, that means this is NW, this is N. So, NW 2 pi by NW must be less than equal to 2 pi by N. Okay. And I said that LW must be 2 pi by B. So, how much dissemination in time is possible? How much dissemination in time? How much dissemination in time is allowable is defined by the omega c, which is the bandwidth of the analysis window. So, if it is Hamming window, then bandwidth B is equal to 8 pi by NW. So, LW should be 2 pi by B is equal to NW by 4. So, 75% overlap. So, LW is equal to 75% overlap, up to 75%. Okay? So, this way we can find out the time and frequency sampling. Okay? So, let us not go, sorry, I have done mistake. This is should be, this should be 2 pi by NW must be greater than or equal to 2 pi by N. This is given in the slide. So, there may be a mistake in once I am writing in the board. Okay. So, time frequency sampling is there. Now, suppose I want to write down that overlap add method in algorithm. So, if you see, if you go through this slide, you can get the algorithm. Okay. So, this is given. By this way you can write a program for your synthesis. Okay. Now, I come to the application of this. So, summary, in summary OLA method, the no time aliasing if window length NW is so that 2 pi by N is less than equal to 2 pi by NW. Okay. And no frequency domain aliasing occur if that omega c is equal to 2 pi by L. So, if 0 are allowed omega c, then condition 2 can be relaxed. Okay. Now, in summary FBS method, the 2 pi by N, this one NW is greater than equal to N. Okay. If 0 in Wn are allowed, then the condition 2 can be relaxed. Okay. So, now I come to the short term Fourier transform magnitude. So, okay, before that we should explain it. So, what I said that x of nk is nothing but a complex number Fourier transform. So, every Fourier transform component has two parts, one is called magnitude and another is called angle phase. So, if it is all component, let us one of the component is written is A into JB in complex number, then magnitude is nothing but a root over square of a square plus b square, and theta is nothing but a tan inverse b by a. So, if I draw this one with respect to frequency, then I call magnitude spectra, which already I have discussed in beginning class. Magnitude spectra. If I draw frequency versus theta, then I call phase spectra. Okay. So, FTM, short term Fourier transform magnitude, short term Fourier transform magnitude. So, only magnitude part we will take, we discard this phase part, we do not use this phase part, and this is many cases it is used for time scale modification and speech enhancement. Okay. Now, it was shown that I am not going details mathematics of STFTM synthesis. So, STFTM analysis is that I do the same analysis and calculate the magnitude part. So, analysis part is okay. So, synthesis part, there is a details mathematics available. I am not going that details. You can go through the books and you can if you want, then you can really you can go through the books and find out the details. So, it is said that from the magnitude part, if I maintain certain constraint, then from magnitude part also signal recovery is possible. So, it is said that from the magnitude part itself I can recover the signal. So, signal recovery is possible if I only take the magnitude part. Okay. So, that if I take the magnitude part, then analysis is called STFTM, short term Fourier transform magnitude, okay, and synthesis is STFTM synthesis. Okay. So, I am not going details on the mathematics. Okay. So, there will be constraint on analysis window and the signal, if there is some constraint is allowed, then it can be shown that from the STFTM also I can recover the signal. Okay. So, I am not reading the slide you can read better than me. So, now come to the application. So, why we do STFT? STFT analysis, synthesis, all kinds of things, why we will do it? That what is the application of STFT? Signal estimation and modification, STFT or STFTM both. Suppose I have a signal Xn that may contain let us 2 kilohertz to 5 kilohertz component. I want to reduce the amplitude of this portion. So, I analyze Xn in frequency domain and reduce whatever modification I want, I modify the spectrum and then take the synthesis again, I will get back the Xn, which is modified signal. Okay. So, I can do it in both terms. I can calculate x of n omega and do the modification in x of n omega, or I can calculate x on n omega and take the magnitude part and modify in the magnitude part, then also recovery is possible. Okay. So, STFT or STFTM is used to signal estimation. So, I want to the sparse spectral magnitude of this estimate, the spectral density of the signal. I can do the estimating, or I can modify the sum spectra, and that then another one is called time scale modification. I can do the time scale modification of the speech signal and noise reduction. Okay. So, time scale modification. Goal, what is time scale modification? I can give you example. I want to either speed up or slow down the speech signal while maintaining the approximate pitch. If you remember earlier that there is a you can say tape recorder, or you can say the gramophone, that the gramophone recorder, gramophone, that disc, gramophone disc. If you see at the top of the gramophone disc, the RPM was mentioned. RPM was mentioned. It is 60 RPM record, it is 40 RPM record, it is 30 RPM record, that is mentioned. During the recording time, the recording speed is mentioned there, so that playing time, if I play the same speed, then only I get the exact recorded signal. If I increase the speed, what will happen? So, suppose there is a 3-second signal is there, now I increase the speed. So, suppose if I increase the RPM, so if there is a 5 track is 3 seconds, now increase the RPM, time will be reduced, speed up, so time will be reduced. So, instead of 3-second song, I can get 2.5 second song, or let us 2-second song. If I modify more, then what will happening? Once I increase the speed, the spectral characteristics of resampling, that is nothing but resampling, spectral characteristics also changing. So, the fundamental frequency of speech is also changing. So, that is why when you play a 60 RPM record in 40 RPM, what will happen? If it is 60 RPM was there, you quickly play it, so fundamental frequency may shifted to female voice. You can do that. So, male voice become female voice become male voice. This is happened in cassette also. If you see the cassette, if your tape recorder is very low, very old, then if the motor speed is changed, then the quality of sound is changed. Okay. So, sometime I want time scale modification. Suppose you experience with the movie, if you know that first you have done that acting and then the voice is synchronized with your acting. Okay. So, suppose when you dub it, that time you found that recorded speech is slower than the movement of the lip during the acting. So, what I want let us recorded speech little bit faster. So, I can play it fast, that much changing the sampling, resampling it, or what I can do, I can cut some portion. Okay. So, that is called time scale modification. So, in time scale modification, cut and paste. Suppose I have, this is my voicing segment. I say something and there is a voicing segment. This voicing segment represent, this to this represent is let us 1 second. If I want to match with the lip movement in the video, I have to make it let us 50 instead of 1 second, I have to make it 0.8 second. So, how can I do it? Either I can cut some portion of the signal and add them. If I cut, then I can paste them. So, if I cut in arbitrary position, what will happen? There may be a pitch mismatch. A half period is cut this side and half period is cut this side. So, there is a pitch mismatch. Okay. Also, if I want to expand it, let us 1 second I want to make it 1.2 second. So, what I will do? I will cut some signal from here and paste it here. So, at that boundary there may be a pitch mismatch in adjacent frame or this boundary. So, there may be a pitch mismatch. So, that is a method, but it is a not good method, but if you cut it precisely, it is a good method. I can show you in next class, if I take, I show you in using a cool edit, I can cut exactly one period of voice and paste it. I can show you how it should be cut. Okay. So, if it cut in arbitrary position, there will be a problem. Then they said, how do I solve it? If you see any speech signal, if you see, if you remember the opening, closure and opening of the vocal fold. So if you see, if I want to see the vowel a, it will look like this, vowel a. So this is a complete period. Again it will be look like this. Now suppose I cut in here and cut in here and cut it out. So what will happen? This is half pitch, this is also half pitch, so that will be pitch mismatch. Okay. So to avoid the speech mismatch, next method is called PSOLA, pitch synchronous overlap add method. Details I will discuss these things during the speech synthesis. PSOLA, TD-PSOLA, ES-NOLA, all we will discuss. So pitch synchronous overlap add method, then they said, if I able to find out the epoch point, the closing and opening point of the vocal hold from the signal, then I can synchronize the pitch. So I can exactly cut one period, then no problem. If I cut one period and paste it one period here, there is no problem. So that is called pitch synchronous. Now to get that exact pitch period from the voice signal automatically is very difficult. So estimation of pitch synchronization, or you can make the pitch synchronization, is very difficult. So that's why this process is also very difficult. Other is called STFTM synthesis. To avoid speech synchronous problem, use only the magnitude spectra of the frame. From the magnitude spectra, it is possible to synthesize the speech signal. So compute x of nl omega at appropriate frame interval or dissemination rate and appropriate window length and appropriate, you can say, the length of the DFT. Then modify dissemination rate with the new rate m equal to L by 2 to speed up factor by half, and then take the inverse transform and estimate the signal. So STFTM I can use to time scale modification of the speech signal. If you see it here, so this is dissemination in time in L. So this is L, 2L, 3L, 4L, 5L, 6L. Now once I synthesize time, I make the dissemination time is L by 2. So it is half, M, 2M, 3M, 4M, 5M, 6M. So I can say squeeze the number of samples, so I can speed up the signal. If I want to slow down the signal, so instead of half, I can say 2L. So it is double. Okay. So this way I can do the time scale modification of the speech signal, which is the application of STFTM. So this is the block diagram. Okay. Next one is the noise reduction. You know that in Cool Edit there is also a button called noise reduction. So suppose I have recorded a signal, speech signal, this silence, then I start recording, this portion I have not speak anything, then I start speaking. So the noise in the silence region also is here, in noise also there. So noise is heard some much during the speech and the speech is going on. I want to remove the noise. If I consider the noise is stationary signal, that means noise is not changing over the signal, then I can estimate the noise power from this silence zone and subtract it from the spectral information of this speech, and again resynthesis, I can remove the noise. So what I will do, I first estimate the noise power by analyzing this portion, take a single window on this portion, and I can estimate that n omega. Then I apply that noise estimation. So noise estimation is, let's SB, SB is the noise estimation. So, I can subtract the noise estimation from the signal, spectral estimation, and I resynthesis it, I can get back the signal, the noise is removed. Okay. So, this way there is a lot of algorithms you can develop. So, there is a algorithm, there may be a complex procedure I can find out, I can estimate the noise in different way, I can subtract not full. So, what is the problem is that if this is a noise and speech signal contains a sibilant sound which is also a noise, if I subtract it, the sibilant sound may go. So, this is the problem. So, then lot kind of estimation I can say, okay, if this is a sibilant sound, then do not subtract this. So, those kind of algorithm I can write and I can remove the noise from the speech signal. Okay. So, STFTM can be used, or STFT can be used for noise reduction, time scale modification, speech enhancement, all those things. Only things is that resynthesis is done by OLA method, overlap add method, or FBS method. OLA method is recommended. You can write an OLA method algorithm to reconstruct the, because I have to get back the signal again. Okay. Only reconstruction is only possible if I suitably choose the window and also the shifting of the window. So, that is why if you see in any parameter extraction we do the frequency analysis of the speech signal, what we done. So, suppose I have a long speech signal, this is 4800 sample which is 16 kilohertz sampling rate and 3-second signal. So, I have that number of sample. We have not taken all sample at a time and do the frequency analysis. What I will do, we will divide this signal with a frame rate and window length. So, we choose a window length, analysis window NW is equal to let us 20 millisecond. Okay. So, NW is equal to 20 millisecond. Okay. Then what we will do, one kind of window we use, either Hamming window, Hanning window, or rectangular window, any kind of window we can use. Okay. Depending on the window that define me the omega c. So, L is equal to 2 pi by B. So, that define me what kind of shifting is possible. Then I shifted the signal that way, then take another window from here to here. So, if it is 10 millisecond is shifting, so this is 10 millisecond. So, again 10 to, so this is 10 millisecond, this is 20 millisecond. So, I can first window is 0 to 20 millisecond. So, first window, first frame, frame 1, 0 to 20 millisecond. Second frame, 10 to 30 millisecond. So, I take 10 to 30 millisecond. Third frame, 20 to 40 millisecond. So, I can instead of millisecond, I can number of sample I can do. Okay. So, I said 100 frame per second, that means the shifting of the window is 10 millisecond. If I say I want 200 frame per second, shifting of the window I can easily understand 5 milliseconds. So, that is why we have do the speech processing in frame. Then I can do the STFT, I can use the OLA method to get back the signal. So, I analyze the signal like this way. If you see, there is a picture I have shown you, you can go through this slide also, this one. So, I take frame by frame, 70, I can make 75% overlap also. I analyze frame, I get back. So, those are the inverse Fourier transform, I get back the frame. Then I add all those frame, I get back the signal. Okay. So, this is the overall STFT analysis. The STFT M synthesis is, I have not described. If you want, you can you can just, I want that if you raise in the forum that STFT-M also required, or you can go with that book which I have referred, that book you can go with the mathematics. And if you want, I can take another half an hour class in the end, because time will be not permitted to details go to STFT-M. Okay. So, it is nothing but a mathematics, all kinds of mathematics deduction will be there. So, you just go through the book. If you not understand the deduction, then again I come back. Okay. Thank you.